This lesson is going to be on chemical bonds, and the whole purpose as to why chemical bonds happen, why they occur, and so that's what we're going to look at here. Chemical bonds, a strong attractive force between atoms or ions in a molecule or a compound. Now there's two bonds that we're going to talk about. One of them is called an ionic bond. We're going to talk about ions in a second. And the other one's going to be called a covalent bond, where they share electrons. So when electrons can be transferred or they can be shared. All right, and there's a, well, I'll go over it in a minute. Compounds form. When compounds form, and we talked about this already. I talked about it back in the very first unit we did in this semester. We talked about how elements and compounds are very different. You take sodium chloride, for example. Sodium, shiny metal. Chlorine, poisonous gas. You mix it together, and bam, you get table salt. Very different substance. Very different substance are created. So it says compounds form. Properties aren't anything like those of the individual elements. They're very different. Right? They're completely different. And sodium chloride is the best example because it's something we use all the time. We don't even think about it. But it's very different. A chemical formula. A formula is when elements that make up a compound and the exact number of atoms in each element in a unit or compound. So a chemical formula is showing two or more elements bonded together. All right, an example of that would be like H2O. Now, when we read a chemical formula, what we want to look at, it says H2O. Well, we know H on the periodic table. If we pull up H, we don't look at anything else right now. We just look at H. It's hydrogen. All right, and the little 2 there we're going to get into, that's called a subscript. All right, this is called a subscript. All right, that tells us how many hydrogen atoms are in an element. All right, so when there's a subscript 2 like that follows the capital letter or the element, that tells us how many are there. So H2O. So there's 2 hydrogen atoms that bond with 1 oxygen. All right, and you might say, well, how do you know there's 1? You don't write 1. It's just assumed. If O is there, you don't write 1 afterward. All right, so if it's H2O, if there's no subscript there, we just know it's 1. You don't have to write 1. I don't want you to write 1 because they don't write 1. It's just assumed that it's 1. All right. And once again, and I talked about this in the last unit, kind of a little bit toward the end. I said it's very important for us to write formulas correctly when you guys write formulas, because CO, that's cobalt. This is cobalt. That's a transition metal. This is carbon monoxide, and we're going to get into how to name these. All right. Monoxide. This is carbon and oxygen bonding together. All right, so those are 2 very, very different things. So make sure if it's a capital letter and a lowercase letter that you write it exactly as it shows. If you're trying to show a bond of carbon monoxide, make sure you write it as 2 capital letters. If you're showing 2 elements bonded together. All right, and same thing here. Like here's another example. SiO. Well, if this is silicon dioxide, which is a fancy word for sand, SiO2, the top example here, this top example, that shows us, that would tell me that sulfur, iodine, and oxygen are bonded together because there's 3 capital letters. This will tell me silicon dioxide. All right, because there's Si, the I is lowercase, so I know that it's attached to the S since it's lowercase. All right, so that's silicon dioxide. This is 3 separate elements up here. All right, so once again, just another example. Make sure you're very particular. All right, a subscript written below. All right, think of like submarine, sub-level, all right, whatever you got to think. Subscript means it's written below, because we are going to write superscripts also later on, but a subscript, like a submarine, goes below the water. It's written below. That will tell you how many atoms are in an element, in each element of a compound. And it says if no subscript is written, then that unit only contains 1 atom of that element. So like carbon monoxide up here, there's no subscripts, 1 carbon, 1 oxygen. Over here, silicon dioxide, 1 silicon, 2 oxygen. Right, so we just count the subscripts. All right, and we're going to get it. We'll talk about that a lot. Atomic stability. All right, electric forces, oppositely charged electrons and protons hold atoms and molecules together. The forces are going to cause compounds to form. The noble gases, we introduced this in the last unit. Noble gases, they are stable. Once again, these are the cool kids on the block. We're going to talk about every element, every atom, element, whatever you want to say, wants to be like the noble gases because they are atomically stable. All right, they are unusually stable. All the other elements, when they bond, want to be like them. All right, and the rule that we talked about, we introduced this last time, is the octet rule. You're going to have to know this. I don't know another way around it. Most atoms form bonds in order to have 8 electrons in the outer shell. All right, just like neon here. All right. 8 electrons is the goal. That's the whole point. We want to get to 8 electrons in the outer shell. So when we form bonds, when we write our chemical compounds, what we want to get to is 8 in the outer shell. The exception to those would be like the early elements, like hydrogen. Hydrogen wants to be like helium because remember that first energy level, if you remember, the first energy level can hold 2 electrons. All right, and that is a full energy level for just that first. But every level after that, it fills with 8. So our goal is to get to 8. The exception to that rule is the first few elements. All right, and stability is the driving force behind bonding. Stability is the driving force behind bonding. This is why atoms bond, is to get stable, to get a full outer shell. All right, to get a full outer shell, that is why bonding occurs, to reach that atomic stability. Once again, we're going to talk, like I said, a lot about electron dot diagrams. This is what we want all our electron dot diagrams to look like. The only exception to that is helium. Helium has 2 dots above it. When the dots are written together like that in a pair, that means that the first level's full. The first energy level's full. All right. And those are all the unique noble gases. You can see they're all filled with 8. We want to get to that point where everything's filled with 8. All right, obviously, the exception to that's going to be like hydrogen, lithium, etc. So hydrogen has 1 dot. Its outer energy level is not full. It wants to be like helium because helium's got 2 dots, so it's going to form bonds to get to the point to where, that's why it bonds with oxygen, because it can get to that full outer shell when hydrogen and oxygen bond together. All right, and we've already talked about this. Let me see. We talked about how the group determines the valence electrons. We just got done talking about this, so this is the periodic table. This is the 1, 2, we skipped a dip, 13, 14, 15, 16. Remember, these all have, if I zoom in on these, lithium, sodium, they all got that 1 electron in their outer shell. They all got that 1 electron in their outer shell. These have 2 electrons, all these elements in group 2. Now, the key thing is, and you can see the color of these, a lot of times we don't deal with colored ones. Metals are going to be much more likely. Metals, this is the blue. I'm looking at the blue shade, the background. Metals will lose electrons. I don't remember if I got that later on this one or not. All right, but metals are going to lose electrons. All right, and the reason why metals are going to lose electrons is because if you look at them, we want to get to a full outer shell, right? Well, it's going to take a lot less energy for them just to lose, like for example in sodium, to lose just that 1, because if it lost this just 1 electron, if it gave it away, look, that next energy level's filled with 8. Perfect. If magnesium lost those 2 electrons, look, its energy level is filled with 8. All right? And so, and lithium, if it can lose those 2 electron, or that 1 electron, excuse me, its next energy level, remember that first energy level can only hold 2, so that's okay, that's a full shell. Same thing with beryllium. All right? So if it can lose those electrons, it's a lot easier for it to do that. It takes a lot less energy. Whereas our nonmetals, all our nonmetals need to gain If you look at fluorine, 1, 2, 3, 4, 5, 6, 7. It just needs one more, so it's going to try to steal one from one of the metals. Because the metals are like, hey, anybody need an electron? Fluorine's like, yeah, I do. That's exactly how the conversation goes too. And oxygen, you can see oxygen has 6. It's going to be a lot easier for oxygen to gain 2 than it is going to be to lose 6. All right, so we're going to talk a lot about that. But that's the whole point of bonding. So like lithium and fluorine, for example. And this is why sodium and chlorine bond so well. Because if you look, sodium, once again, our goal is to get to 8 electrons. Sodium's like, I got an electron, who needs it? Chlorine's like, yo, hey man, I could use one. All right, so sodium's like, here you go, bro. And so sodium then will transfer its electron to chlorine, and then they become unlike charges. All right, they become opposite charges and they attract. And we're going to talk about that more when we talk about ionic bonding. But then they both have a full outer shell, because if chlorine can take the electron from sodium, they have a full outer shell. Same thing. That's why group 1 and group 17 bond so well together. Because 1 has 1 electron. All the elements in group 1 have 1 electron in their outer shell. They got 1 that they can get rid of. All the elements in group 17 need 1 electron. So group 1 and group 17 form bonds readily. Group 2 and group 16 do also. All right, and so we're going to really just focus on groups 1 and groups 2. All right, we're going to focus on these two, and 16 and 17 when we create bonds. All right, when we write bonds. We'll get into 15 a little bit, but not much. How does hydrogen or any other element try to become stable? Gain or lose electrons its outer shell, combining with other atoms that have partially completed outer shell. As a result, each will achieve stability. So here's an example. Transferring electrons. All right, and once again, this is called an ion. So sodium will transfer its electron to chlorine. All right, and then sodium, if you look at the periodic table, sodium's atomic number is 11. So if you're like, where do you get 11 from? Sodium has 11 protons. Because if you take the atomic number, it has 11 protons. But if it gives its electron away, it'll only have, remember, electrons are negative charges. So if it gives that electron away, it'll only have 10 electrons. So as a result of that, and this is where it gets kind of confusing because sodium's losing something, but it becomes positive. A lot of times we think of something being positive because it's gained something. But you got to ask yourself, remember, what is it losing? It's losing a negative particle. All right, so it now has 11 positive charges and only 10 negative charges. So as a result, it's losing a negative charge, so sodium becomes positive. All right, and so that's called an ion. Once again, and more specifically, it's called a cation. It's going to become a cation. A cation is a positively charged element. All right, because it has more protons than electrons. Chlorine, you might think, well, it's adding something, so you think it'd be positive. No, it's adding an electron, but it becomes negative because it is gaining a negative charge. It now has 17 protons and 18 electrons because it gained that electron from sodium, and that's called an anion. All right, it's an anion. It's really easy to remember if you're a cat person. A cation is a positive ion. Right. An ion is just when an atom has more or fewer electrons than protons. All right, when there's a different number of electrons than protons. All right, so a cation is positive. If you're a cat person, that's easy. Like, oh yeah, cats, I love them. It's hard for me because I hate cats. I couldn't care less about cats. But hey, you know what? In this world, I can pretend, hey, yeah, cats are cool. Nah, I hate them. That's how I feel. Deal with it. Some of you are like, I can't believe him. How dare he? Anyway, so that's an example of that. We'll talk about covalent bonding later too, because atoms can also share electrons. Because if I colored this one in, like chlorine when it bonds with itself, oh whoops. He said, hey man, I got 7. Oh, you got 7? Well, hey, let's just share this one. All right, so the chlorine then will bond with, geez, I keep hitting the wrong thing. Will bond with the other chlorine. And then that will become stable, and then this will become stable. They'll share a pair of electrons. And that's called a covalent bond. Up here, what happens is an ionic bond. So they can either share electrons, which is a covalent, or they can... Oop. I don't know why that's weird. Sorry. All right, and once again, we draw electron dot diagrams because it's easier to show that bond between sodium and chlorine. All right, so once again, the whole point is stability being reached. We want to have a full outer shell. When that comes over here, we want 8 electrons, and then we want this one to have, it's going to have none, but really remember that next level's filled. Because remember, you can't go to the third level without the second level being filled. So even though it looks like, oh, sodium doesn't have any electrons, it does. It has 8 in that next level. All right, when you draw a dot diagram. All right. So atoms gain, lose, or share electrons in order to become stable, and that is the whole point behind bonding, is to have stability become reached. All right. And then once again, an ion is a positive or negatively charged atom, and we'll talk about that in more detail later.